Good morning all of you. So we are discussing the nitrogen family. So in the last part of the video we already discussed the general properties of nitrogen family. So like atomic size, ionization enthalpy, electronegativity, density, melting point, boiling point orders, catenation power, and about the nitrogen also we discuss the preparation methods of nitrogen, the properties of nitrogen. Okay, so likewise we discussed a few concepts earlier in the last part of the video. Now in this video we are going to discuss clearly about the hydride of nitrogen family, that is most important hydride, that is the ammonia. Okay, ammonia. So ammonia general formula is NH3. So this is also we call as a hydride of nitrogen. So before I start this ammonia, I just give a small brief introduction about the hydrides of nitrogen family. So let us see. So how the hydrides of nitrogen family will produce? Whenever the nitrogen family, any element, nitrogen, phosphorus, arsenic, antimony, bismuth, any of the 5th A group element, when these elements are reacts with hydrogen, we get EH3 type of hydrides. So what type of hydrides they produces? EH3 type of hydrides. For example, NH3, PH3, ASH3, likewise EH3 type of hydrides generally the nitrogen family will produce. And when you see the properties of this EH3, means hydrides of 5th A group elements, the first property about their basic strength. So I'm just writing the all hydrides of 5th A group elements, that is NH3, PH3, ASH3, SBH3 and BIH3. These are the 5 hydrides of 5th A group element. When you compare the properties of these 5 hydrides, let us see. The first one, their basic strength. What is the order of basic strength of the hydrides of these 5th A group elements? So when you compare these all, ammonia is the strongest base, whereas bismuthine is least basic in nature. So that means the basic strength decreases down the group. The basic strength decreases down the group. So that is NH3 greater than PH3, ASH3, SBH3 and BIH3. So what is the reason? Basic strength means what? What do you mean the basic strength? The ability of donating the lone pair of electrons is called what? Basic strength. So in case of ammonia, the central atom is what? Nitrogen. It's the smallest size atom among the all. This is the smallest size of atom. So within the smaller area, same number of pairs of electrons, 1 pair of electrons are present. That means the electron density is high in case of ammonia. So if the central atom having high electron density, it can easily donate the electron pairs. Whereas when you go from nitrogen to phosphorus, phosphorus to arsenic, what happens? The size increases. If the size increases, electron density decreases. If there was a less electron density, automatically the ability of donating the electrons is less. So that is why the basic strength decreases down the group. About the hydrides. The next one, coming to the hybridization, are bond angles. Bond angles. What happened to the bond angles here? Here bond angles decreases down the group. Decreases down the group. See, if you see the bond angle of in ammonia, that is nearly 107 degrees, whereas phosphine is 92.7 and arsenic is 92 degrees, SBH3 is 91.5 degrees and bismuthine is nearly 90 degrees. So almost these all are having nearly 90 degrees bond angle, whereas ammonia having 107 degrees. So what is the reason? If you see the hybridizations of these central atoms, in ammonia, the central nitrogen atom is sp3 hybridized. sp3 hybridized. Generally, sp3 hybridization having the general bond angle is 109 degrees 28 minutes. But because of presence of a lone pair, the bond angle decreasing from 109 degrees to 107 degrees. Coming to phosphine, arsenic and stibine and bismuthine. In the remaining hydrides, the central atom is never undergo hybridization. The pure p orbitals are involving in the bonding. If pure p orbitals are involving, generally the p orbitals are perpendicular to each other, so their bond angles are nearly 90 degrees. So their bond angles are almost equal to 90, but not exactly equal to 90, so slightly decreasing from 92.7 to 90 degrees. This data is not accurate. I'm just giving you the example for that. So this is about the bond angles. Next one, stability. Stability of these hydrides. Generally, when you go from ammonia to bismuthine, from top to bottom, bismuthine, the stability decreases. The stability decreases. So what is the reason why the stability is going to be decreased? Why? Because in NH3, this is the NH bond. Whereas in bismuthine, BiH. So when you compare the bond lengths, the NH bond length is shorter, whereas the Bi and H bond length is longer. If there was a longer bonds are weaker. So we can easily break this, whereas this one is, this bond is stronger, so it's very difficult to break it. That is why when you go from ammonia to bismuthine, what happens? The stability of them decreases. So NH3 is more stable than PH3, then ASH3, then SbH3, then BiH3. This is the order of stability. Coming to the reducing nature. Reducing nature means what? The ability of releasing H plus or hydrogens. See, if the stability decreasing, so which can easily release the hydrogen? Bismuthine can easily. Why? Because this bond is longer. If it is longer, this is a weaker bond. If it is weaker, we can easily break it and can release the hydrogens. So the reducing nature increases by going from ammonia to bismuthine. So coming to the reducing nature increases down the group. So this is about the reducing nature. Next one, boiling point. If you see boiling point, the order of boiling point slightly varies. Generally, when you go from top to bottom, the boiling point generally will increases. But in this case, PH3, ASH3, ammonia, SbH3 and BiH3. Ammonia is exceptionally having higher boiling point than phosphine and arsenic, because in ammonia, this ammonia having the ability of making hydrogen bonding. Because of the ability of making hydrogen bonding, the ammonia having higher boiling point than phosphine and arsenic. Okay, so this is about the boiling point. Coming to the melting point. Ammonia is exceptionally having higher melting point than remaining all. So this is the melting point order, this is the boiling point order. So this is a general properties we should know before we start about the ammonia. So now let us start the preparation methods of ammonia, the properties of ammonia, and what are the how to distinguish, how to test the ammonia, presence of ammonia. What are the tests we are using to detect the presence of ammonia? Now let us start the preparation methods of ammonia. So the first method of preparation from urea. How can we prepare the ammonia from urea? So if you take the urea by hydrolysis. Simply by hydrolysis, we can prepare the ammonia. Let us see. Urea general formula is NH2CO NH2. This is the general formula of urea. This is also we call as a diamide. Why? Because CONH2 is a functional group of amide. This is one amide functional group. This is another amide functional group. So it's a combination of two amides. So that is why urea commonly we call it as what? Diamide. So when this urea on hydrolysis, if you add water to it, so we generally will get 2 moles of ammonia with the liberation of CO2. So this is the first method and the easy method for the preparation of ammonia. The second method, from ammonium salts, preparation of ammonia from ammonium salts. So in generally there was a lot of ammonium salts available in the earth crust. By taking that ammonium salts, simply by heating or by thermal decomposition or by treating them with a strong basis, we can easily prepare ammonia. Let us see. So from ammonium salts, in 2 ways we can prepare. So by thermal decomposition, we can prepare ammonia. That's the one way. And another one is by heating with strong bases. By treating them with a strong basis, we can prepare. Let us see both the ways with one example. See, ammonium salts. Here I am taking, what are the examples for ammonium salts? We can take NH4Cl, or else ammonium sulfate, or else ammonium carbonate. So likewise, there are so many of examples for the ammonium salts. You can take any one. Now I am taking NH4Cl here. When this ammonium salts, when this ammonium chloride, this on heating, if you heat the ammonium chloride, so what will happen? We will get NH3 plus HCl. Simply by the heating to very high temperature, the ammonium salts are liberating what? Ammonia gas. It's an easy method. Or else, when to this ammonium salts, if you add strong bases like NaOH or CaO, MgO, likewise. See here, I am adding CaO here. To this ammonium salts, if you add CaO, we will get NH3, CaCl2 plus H2. CaCl to balance, 2 chlorines, calcium balance, 2 nitrogens balanced, and H2. So this is when the ammonium salts are treated with the strong bases like CaO, MgO, or else NaOH, CaOH twice, MgOH twice. You can take any of these strong bases. When we treat them with the strong bases and heating, okay, after we mix the strong bases to the ammonium salts, after the heating we get ammonia gas. It will liberates ammonia gas. So this is the second method of preparation of ammonia. The third one, from nitrites. From nitrites. So from nitrites, how? By hydrolysis. Nitrites on hydrolysis, we will get the ammonia. So here I am taking calcium nitride, Ca3N2, calcium nitride. So nitride means the nitride generally having -3 charge. Remember that. So if the nitrogen having -3 charge, then that ion we call it as what? Nitride ion. Not nitrite, nitrate. They are different. This is a nitride. So when the calcium nitride on hydrolysis, we will get this nitrogen will come out as what? Ammonia. And this calcium will come out as what? Calcium hydroxide. Calcium hydroxide. See, 3 moles. For that we need 6 moles of water molecules. So this is a simple method. Simply you take any nitride. When nitrites on hydrolysis, we get ammonia and also calcium hydroxide. So this is the third method of preparation. And the fourth one, from azides. Azides. So what is azides? Azides general formula N3 minus. See, N minus 3 is nitride, N3 minus is azide. Okay, when these azides, for example, I am taking sodium azide, NaN3, sodium azide. See that when sodium azide on heating, suppose if you heat the azides, in the preparation method of nitrogen also we discussed. When the azides are on heating, we get nitrogen gas. So azides are heating, what we get? Nitrogen. The same azides, instead of heating, if you hydrolyze, on hydrolysis of azides, what we get? Ammonia we will get. Understood? Remember this point. Azides on heating we get nitrogen, whereas azides on hydrolysis we get ammonia. Okay, so this is a fourth method. And the fifth one, there were some commercial methods, industrial methods are there. 2 methods. What are the 2 commercial methods or industrial methods? So why we are calling these 2 methods as a commercial? Because if you wanted to prepare in a bulk amount, there was a huge demand for the ammonia. So in most of the laboratories, industries, they need ammonia. So to get the ammonia in bulk amounts, we follow these 2 methods. That is why we are calling them as a commercial methods. And the first one is cyanamide process. And the second one is Haber's process. Cyanamide process, Haber's process. So let us see these 2 processes one by one. The first one, cyanamide. Yes, cyanamide process is a multi-step process. No? If you go in a many steps, then only we can finally get ammonia. Let us see. In the first step, they will take limestone, CaCO3. When limestone are heating, what we will get? CaO plus CO2. CaO, lime we got. Now, to this lime, if you add charcoal or coke, you add carbon to it. When we add carbon to this lime, what we get? We will get CaC2 and carbon monoxide. So what we call is calcium carbide. Calcium carbide. Then when this calcium carbide mix with nitrogen, we will get CaCN2, not CaCN twice. CaCN2 twice means calcium cyanide, that is different. This is the CaCN2 plus carbon. And this mixture, the mixture of this is what we call as, this is alone we call as calcium cyanamide. And this is a carbon. So the mixture of calcium cyanamide plus coke or carbon, this mixture we call it as what? Nitrolime. So now this nitrolime mixture, you take cyanamide, that is a CaCN2. When this cyanamide on hydrolysis, this is on hydrolysis, okay, we will get 2 moles of ammonia and CaCO3. This is again, you can use it in the first step. So likewise we can prepare ammonia. So nitrolime, the nitrolime is used to prepare so many of other fertilizers, because most of the fertilizers are salts of ammonia only. So this is about cyanamide process. So clear once again, when CaCO3 on heating we get CaO plus CO2, calcium oxide plus CO2. When this calcium oxide, when we mix with the carbon, we will get calcium carbide. To this, when you add nitrogen, we get CaCN2. Finally, calcium cyanide plus carbon, that is what we call a nitrolime mixture. And this nitrolime mixture on hydrolysis, we get ammonia. And remember that Carbon is mixing with a lime at the temperature of 2273 Kelvin, that means nearly 2000 degrees Celsius. Whereas here we will maintain 1000 degrees Celsius. Okay, here 2000 degrees Celsius, here 1000 degrees Celsius. Okay, so in the third step we can also use a CaF2, CaCl2 as a catalyst also. Why? Because they promotes a reaction, rate of reaction. So this is about the cyanide process. The second one, that is about Haber's process. Haber's process. As we know, this is a well-known process, a method of preparation of ammonia. How can we prepare? So that is when nitrogen mixed with a hydrogen in the ratio of 1:3. When one volume of nitrogen is mixed with 3 volumes of hydrogen, we will get ammonia. Okay, by maintaining high pressure. By maintaining high pressure, and the temperature is optimum temperature, and a catalyst, iron as a catalyst. What is a catalyst in Haber's process? Iron. And molybdenum or K2O or Al2O3. You can use any one of these three. So molybdenum, potassium oxide or alumina, any one of them as promoter. Okay, so but by maintaining these conditions, we will get ammonia, and during this process, del H value is minus 92 kg, kilojoule per mole. So exothermic process. You may get the doubt. According to Le-Chatelier principle, for all exothermic reactions, low temperatures are favorable. But why we are maintaining optimum temperature is nearly 450 degrees Celsius to 500 degrees Celsius. So 450 to 500 means it's a high temperatures only. Even though the low temperatures are favorable for this reaction, we are maintaining high temperatures, because if you maintain the low temperatures, the rate of this reaction is very, very less. So to enhance the rate of the reaction, even though low temperatures are favorable, but still we are maintaining high temperatures only. And the pressure is nearly 200 atmospheric pressure we maintain. So 200 atmospheric pressure, 450 to 500 degrees Celsius temperature, iron as a catalyst, molybdenum or potassium oxide or alumina as a promoter. When we maintain these conditions, 1:3 ratio of nitrogen and hydrogen will give ammonia. So this process we call it as Haber's process. So these are the methods of preparations of ammonia. Next, move on to the physical properties of ammonia. Physical properties. If you see the physical properties, ammonia is it's a pungent smell gas. Pungent smelling gases, and it is lighter than air. So when we compare the density of air with ammonia, the density of ammonia is lesser, so it is lighter than air. Next one, it can be easily liquefied. It can easily liquefy by applying pressure of 9 atmospheric pressure. Simply, if you maintain the 9 atmospheric pressure, the ammonia can easily be liquefied. And the liquid ammonia boils at minus 38.4 degrees Celsius. Boiling at minus 38.4 degrees Celsius and freezes at minus 77 degrees Celsius. Freezing point is minus 77 and boiling point is minus 38.4. Coming to the solubility, it is highly soluble in water. It is highly soluble in water. So when you send ammonia gas into the water, we will get NH4OH or NH4 plus OH minus ions. It is highly soluble in the water because of producing ions into the water. And one more reason, it is highly soluble in water because of its hydrogen bonding. So due to H bonding, intermolecular H bonding is there between water molecule and ammonia, so that they are highly soluble in the water. And next one, the dielectric constant of ammonia is high like water. Even water is also having high dielectric constant. That is why water is acting as a universal solvent, and most of the this is the ionizable solvent. Similarly, the dielectric constant of ammonia is also high, but less compared to water. But even anyhow, it is also having high dielectric constant. That is why we can use this as an ionizable solvent. We can use this ammonia as what? Ionizable solvent. How? Let us see. If you take 2 moles of ammonia, we will get NH4 plus NH2 minus, self-ionization. But here its Kc value is 10 power minus 30, whereas water is 10 power minus 14. So this is about some physical properties of ammonia. Let's move on to the chemical properties or chemical reactions. Chemical reactions. The first reaction, that is action of heat. Action of heat. If you heat ammonia, what will happen? Simple, reverse reaction takes place. If you heat the ammonia to more than 500 degrees Celsius, more than 500 degrees Celsius in the presence of catalyst like iron or magnesium, okay, in the presence of catalyst, any one of these catalyst, if you maintain more than 500 degrees Celsius, ammonia will decompose into nitrogen and hydrogen. It's a reverse of Haber's reaction. Up to 500 degrees Celsius, ammonia formation takes place. If it is exceeding 500 degrees Celsius, reverse reaction takes place. So this is the action of heating. Next one, action with air or oxygen. Action with air. In fact, ammonia with air, there was no reaction. It will not burn. It doesn't burn in air. But if you supply free oxygen, then it burns with blue colored flame. Because of the producing nitrogen gas, it gives which color? Blue colored flame they generates. So which colored flame? Blue colored flame it generates in the presence of free oxygen. So this is about the action of air and oxygen. Next one, action with halogens. It's very important reaction. Action with a reaction with halogens. So in the halogens you can take anything. Here I am taking chlorine. So action with halogens, this reaction depends upon again the quantities of ammonia and halogens. For example, when ammonia reacts with the chlorine, so now in the first case I am taking ammonia is in excess amounts. So ammonia is in excess. When excess ammonia reacts with chlorine, we get the products as NH4Cl by the liberation of nitrogen gas. Remember that. When you take excess amounts of ammonia and treating with chlorine, we are getting ammonium chloride and a nitrogen gas will liberate. So here 8 moles of ammonia reacts with chlorine, we'll get 6 moles of ammonium chloride and 1 mole of nitrogen. So it was balanced. Okay, so here 8 moles to 3 moles. 8 moles is excess quantity. So that is why when excess amounts of ammonia reacts with the chlorine, we are getting ammonium chloride by the liberation of nitrogen gas. Suppose if you reverse it, suppose if you take chlorine is in excess amounts, then what will happen? When ammonia reacts with chlorine, here chlorine is in excess amount, we get NCl3 with the liberation of HCl as a byproduct. So here NCl3 they use as an explosive. So when NaH3 reacts with chlorine, we are getting NCl3 plus HCl. So 3 moles of HCl total here. 3 moles of HCl and NCl3. So it was balanced. So when you take excess quantity of chlorine, we are getting NCl3. Excess quantity of ammonia, we are getting ammonium chloride. So this is about action with halogens. Next one, fourth reaction. Reaction with metals. Reaction with metals. How they react with metals? In generally, this ammonia can react with only high electropositive metals like sodium or calcium, magnesium. Only high with high electropositive metals only it can be react. Suppose if you take the sodium, when sodium reacts with ammonia, they use sodamide. Sodamide. Amides get getting. Amides. Whereas magnesium treated with ammonia, we are getting nitrites. Magnesium nitrites. So few metals are giving amides and few metals are giving nitrites. Anyhow, when ammonia is directly treating with high electropositive metals, they are giving either amides or nitrites. Next one, reaction with metal salts. Reaction with metal salts. See, metal salts, we are categorizing the metallic salts into 3 categories based on in electrochemical series or reactivity order of metals. In electrochemical series, there are so many of metals, they are arranging in the order of their reactivity. So like potassium, sodium, calcium, magnesium, aluminium, zinc, iron, tin, lead, hydrogen. So the metals which are present all above the hydrogen are strong reactive metals. Below hydrogens are what? Copper, silver, gold, mercury, platinum. These all metals are what? Less reactive metals. So we are categorizing the all metals into 3 categories. Highly reactive metals, less reactive metals, and the metals which are present in the middle, that what we call moderately reactive metals. So I am categorizing the metal salts into 3 categories. Suppose if you take highly reactive metal salts, when they treated with ammonia, when they treated with ammonia, all the highly reactive metal salts are giving what? Amides, metal amides they are giving, and that is blue colored precipitate they are giving. Blue colored precipitate. As we know, in the +1 also, alkali metals, when we dissolve the metals in the liquid ammonia, we are getting blue colored precipitate. Because of that blue color is not because of ion, that's because of electrons, ammoniated electrons. So similarly here, so when you treat the highly reactive metal salts with ammonia, we are getting blue colored solution, that is nothing but amides. Suppose if you take moderately reactive metal salts. Moderately reactive metal salts means we can take either iron or zinc. These two are the best examples for moderately reactive metals. When they treated with ammonia, if it is a zinc, we are getting zinc hydroxide. Okay, zinc hydroxide is what? White colored precipitate. Whereas if it is iron, we are getting FeOH thrice. FeOH thrice, it's a brown colored solution. So likewise we are getting different colored solutions. Okay, so we are discussing the reaction of ammonia with metallic salts. With highly active metallic salts, they produces metal amides. With moderately active metallic salts, with ammonia they produces their corresponding hydroxides. So for example, zinc gives white colored precipitate, whereas iron gives brown colored precipitate. With the less reactive metallic salts, they forms the complexes with ammonia. So less reactive metallic salts like copper, silver, gold, okay, and platinum. So these less reactive metallic salts on reaction with ammonia, they forms complex salts. So this is the reaction with the metallic salts. Next one, reducing nature. reducing nature. The ammonia also shows some reducing behavior. So they reduces the metal oxides into metals. Metal oxides to metal and itself oxidizes to nitrogen. For example, I am taking lead oxide. When lead oxides reacts with ammonia, we are getting lead, and this ammonia will come out as what? Nitrogen and H2. So this is a reducing nature of ammonia. Next, move on to the structure of ammonia. Structure. If you see the structure of ammonia, see in ammonia 3 hydrogens and 1 lone pair on the center nitrogen atom. It means total 3 bond pairs and 1 lone pair. Total number of pairs are 4. If total number of pairs are 4, that is sp3 hybridized. So if it is sp3 hybridized, the regular geometry is what? Tetrahedral. Tetrahedral structure is the regular geometry. But because of presence of a lone pair, so it's a type of what? A is the central atom, 3 bond pairs and 1 lone pair. AB3E type. In case of AB3E type, the tetrahedral geometry becomes what? Pyramidal shape. Pyramidal shape. So ammonia is pyramidal in shape. So if you see the structure, so this is the structure of ammonia with a bond angle. What is the bond angle here? 107 degrees. 107 degrees. And with this NH bond length is 1.016 angstroms. 1.016 angstroms. So this is about the structure of ammonia. Next one, tests to detect. To detect ammonia. Okay, so what are the tests? 2 tests we usually use to detect the ammonia. The first one, Nessler's reagent. Nessler's reagent test. First of all, what is a Nessler's reagent? We should know. So Nessler's reagent is nothing but potassium mercuric iodide. Potassium mercuric iodide is Nessler's reagent. And how to prepare this? We can prepare this Nessler's reagent by mixing KiHgCl2 and NaOH. By mixing these 3, we will get potassium mercuric iodide. So when you add to this ammonia compound, if you add Nessler's reagent, okay, we get brown colored precipitate. Brown colored precipitate. This brown colored precipitate, if it gives a brown color, it confirms the presence of ammonia. If it is not giving brown color, it is not there was no ammonia in it. So what is the reason why the brown color is forming? The brown color is because of the formation of the complex, that is what? Iodide of Millen's base. Iodide of Millen's base. Iodide of Millen's base. So this is HgO NH2I. So this is the complex formula of iodide of Millen's base. Because of the formation of this one, okay, it is giving brown colored precipitate. So this is the one test. And the last one with suppose you take a glass rod dipped in HCl. If you put the glass rod at the mouth of this ammonia, we get white dense fumes. That is because of formation of NH4Cl. This is the other confirmation test for detection of ammonia. So this is about the ammonia. I think you understood this ammonia. Once you go through the textbook, if you have any doubt, just ping me. I will help you out. Thank you.